Hello everyone, I'm Yanzhao Wu, an assistant professor from FIU. I'm happy to present our recent work, exploring model learning heterogeneity for boosting ensemble robustness. Here's the outline. I will mainly introduce ensemble learning and present our two-tier heterogeneous task ensemble framework and experimental analysis. Ensemble learning is a very popular technique. The idea behind ensemble learning is also not complex. It is like us to form a committee to make a decision. It is said ChatGPT is also using this technique. So the first step of ensemble learning is to obtain diverse base models to create a base model pool. There are many ways. For example, we can use different subsets of data to train diverse models. If we would like to use the same data set, we can use different hypermeters or different learning algorithms. The second step is to combine those base models. For example, we can simply use all available N-base models as ensemble team. Then we can obtain the results by using ensemble consensus methods such as sample voting, majority voting, or learn to combine. One example is about adversarial tags. For the benign inputs, the single semantic segmentation model and object detection model can make correct predictions for those two images. However, when we have adversarial tags, it is very hard for people to notice the tiny difference between the benign input and attack input. It will also cause prediction errors for individual models. Therefore, even well-trained individual deep learning models are vulnerable when they are deployed in the real world. In the meantime, the Netflix example also shows a potential mitigation strategy. The PDG attack was performed to attack the semantic segmentation model, which has little impact on the object detection model. Therefore, we could defend against those attacks by using a model from another learning task. There are two benefits of using ensemble learning. First, ensemble teams can improve the overall prediction performance. Here's one example from the COCO dataset. Second, ensemble teams are robust against adversarial attacks. Here's a previous TOG attack example on the VOC dataset. The ensemble of 3 object detectors can successfully defend against this adversarial attack. We propose a two-tier heterogeneous task ensemble framework. The first step is to select high-quality ensemble teams for multiple base models using focal diversity. We can form Tier 1 ensembles. They are composed of heterogeneous DNNs for solving the same learning problem, for example, image classification or object detection. We can also build two-tier ensemble to combine heterogeneous DNNs for solving different learning problems, for example, object detection and semantic segmentation. Then the input images will be processed by those models for improving the prediction results. Here, we also need to convert the semantic segmentation outputs into object detections. Next, we use ensemble consensus methods for object detection to aggregate the object detection results. One of the key benefits of ensemble learning is to reduce the vulnerability of a single DNN model, that is to enhance overall robustness. In this paper, we formally define ensemble vulnerability as the expected noise change based on a bounded change delta on the input, such as adversarial perturbations. We formally proved a theorem that the ensemble vulnerability under adversarial attacks is proportional to the equation in this side. Here we assume that ensemble models are independent and identically distributed. The ensemble vulnerability depends on two factors, the team size n and the memo model correlations. For an ideal case, all memo models are independent with their correlations at 0. The ensemble vulnerability can be effectively reduced by increasing the team size n. The ensemble robustness can be improved by increasing the number of independent ensemble memo models. For the worst case, all MMO models are perfect duplicates with their correlation as 1. Their normal vulnerability remains the same as a single DNN. Therefore, it is very important to identify a way to compose abnormal teams with no correlations among MMO models. We develop a focal diversity for object detector ensembles to tackle this problem. This slide shows a comparison of kappa and focal diversity on the Suffer10 dataset. We have 10 base models on Suffer10. We tested all possible ensembles with their size ranging from 2 to 10. That is total over 1,000 ensembles. Different colors in the figure indicate different ensemble team sizes. One fundamental problem is that even though the existing kappa diversity is developed to capture the negative correlation among MMO models for an ensemble team, it fails to reflect that. Here we can see that the ensemble accuracy is not good at all. This issue is also commonly recognized in the literature. We proposed a new ensemble diversity measure called focal diversity to address this issue. The focal diversity allows us to more precisely capture the negative correlation among MMO models for an ensemble team. So now you can see that the high focal diversity scores will give you high ensemble accuracy. In this paper, we apply focal diversity into object detector ensembles to identify high-quality ensemble teams. Here's a base model pools for 2 benchmark datasets, MS COCO and Pascal VOC. The best model for COCO dataset is Model 3 with 52.2% MAP. For VOC dataset, the best model is Model 2 with 81.48% MAP. Object detection involves multitask learning for locating objects with bounding boxes and classifying objects. We develop an ensemble consensus method for object detector ensembles. It includes 3 steps. First, we perform objectiveness consolidation to build a graph for detected objects. Each node represents a detected object. Each edge connects 2 objects with overlapped bounding boxes, and edge weight as intersection over union over U. Second, we aggregate the set of highly overlapped objects detected by different member detectors. Third, we leverage soft NMS to handle multiple overlapping objects of the same class label. We can first look at the Type 1 heterogeneous ensemble performance on the COCO dataset. First, multiple sub-ensembles of size n can be composed from the 6 base models. We can rank those sub-ensembles of size n by their focal diversity scores. Here, we show 2 extreme example ensembles for each team size n. One is an ensemble of high focal diversity in bold, which will be selected, and another is an ensemble of low focal diversity, which will be avoided. Second, the ensembles with high focal diversity also achieve high MAP. The high diversity ensembles can effectively improve the MAP by 1.5% to 2.1%. For example, 124 achieved the MAP of 53.6%, improving the MAP of the low diversity ensemble 012 by 2.1%. Third, all ensembles of high focal diversity outperform the ensemble made of all 6 detectors for COCO and the best base detection model detector RS by 1.2% to 1.7%. The takeaway from here is that Tier 1 heterogeneous ensembles of high focal diversity can achieve high MAP. Here are 2 visual examples for Tier 1 heterogeneous ensemble on MS COCO. First, the ensemble of 3 object detectors, 124 with high focal diversity has higher MAP compared to any of the sub-ensembles of 2 detectors. Second, the MMO models in the low diversity ensemble 12 tend to make similar mistakes and often fail to repeal each other's prediction errors, unlike the high diversity ensemble twofer. This is the motivation for the two-tier ensemble of the heterogeneous learning tasks. We have 3 object detectors and 3 example images. The majority of object detectors make partial mistakes. Hence, the ensemble of those 3 object detectors will also output partial prediction errors. Here we can add one additional model into the ensemble team. It is from another learning task, semantic segmentation. Now, we can correct those mistakes and obtain the correct predictions. Given that the models from different learning tasks have different output formats, the key challenge here is how to convert them into the same representation space for performing ensemble consensus. In order to convert the semantic segmentation outputs into object detections, we use a connected component labeling algorithm to detect those connected components. Then, we can use the boundaries of those connected components to determine the bounding boxes. Next, we average the classification confidence scores from semantic segmentation to obtain the confidence scores for objects. We can use the same semantic segmentation label as the object label. Therefore, the semantic segmentation outputs can be converted into the object detections. Now, we can use semantic segmentation models in the object detection ensembles. We then look at two-tier heterogeneous ensemble performance on a VOC dataset. First, all high-diversity ensembles significantly outperform the low-diversity ensembles in MAP by 0.88% to 6.04%, and improve the best base model unit V3 of 81.48% MAP by 1.78% to 2.95%. Second, the high-diversity two-tier heterogeneous ensembles, that is 0, 1, 2, 3, 5, and 0, 2, 3, 5, including the semantic segmentation model 5, deep level V3, can further improve the high-diversity tier 1 ensembles, for example, 0, 2, 3 in MAP. Here are the measurements under adversarial tags. For the benign scenario, the MAP of the single object detector SSD is 73.11%. The 3 ensemble teams already achieve very high MAP of over 84%. When one object detector is under the adversarial tag, ensemble teams can effectively defend against it. This table shows the experimental results of 2 different adversarial tags, TOGV vanishing attack and TOGN mislabeling attack. First, adversarial attacks can cause a drastic drop of MAP for this well-trained victim object detector SSD, reducing the MAP from 73.11% to 0.66% to 44.93%. That is over 28% reduction in MAP. Second, the 3 ensemble teams can significantly improve the MAP under both benign and attack scenario by 1.16 to 100.98 times. In particular, the heterogeneous task ensemble of 3 object detectors and 1 semantic segmentation model can constantly deliver the highest MAP. Here are the 2 image examples for adversarial attacks. The 2 images in row 1 and row 3 show the detection under benign scenario, and the second rows in the TOGM mislabeling attack. The last row shows the effect of TOGV vanishing attack. Overall, the attacks can cause a victim model SSD to mislabel the objects or fail to detect them. But the transferability of such attacks to other models is known. It shows why ensembles of multiple models can strengthen the overall robustness. That's all my presentation. Thanks. Here's my email and webpage. Feel free to contact me if you have any questions.